Let's talk about this thing called the characteristic equation. So in the previous section, we looked at how to find the eigenvalues if you know the eigenvectors, or how to find the eigenvectors if you know the eigenvalues. But we didn't ever get the fundamental question, which is if you just have a matrix, how do you find both the eigenvalues and the eigenvectors? So let's start with this one in just a small example, and I think that will illustrate the general process for us. So find the eigenvalues and eigenvectors for this thing. Keep in mind what we are looking for if this is an A. What we're looking for here is A times some eigenvector, x, equals an eigenvalue, which we usually call lambda, times that same eigenvector. So we've got two things to solve for. Normally when you're trying to solve an equation, you got two unknowns. That's not enough information. But this isn't just single constants and variables here. We've got a lot of information in that A, in that matrix. So let's make use of that. So we've already looked before in the last section at the algebra here. The typical way to solve for something when it shows up twice in an equation is to move everything to one side, keeping in mind that's a zero vector, and then we factor, and you can't really do a matrix minus a constant, but you can factor with the 1 in there, the placeholder that needs to be there, the I, the identity matrix. So in general, the question of finding eigenvalues and eigenvectors means solving this homogeneous system. Not only for the x, but we also need the lambda, right? But do keep in mind that this guy right here, once we crunch it down, is just a single matrix. So we are really trying to solve a matrix times x equals 0. We're trying to solve a homogeneous system. Of course, there's one solution in general to homogeneous systems right away, which is to let the x vector be the 0 vector. That's the trivial solution. We've already said here that an eigenvector can't be the 0 vector, so that's out. So we need other solutions besides just the 0. And keep in mind what that means. That means there'll be more than one solution, which technically means there'll be infinitely many solutions, which means a bunch of stuff. Remember the invertible matrix theorem? I'm sure you do. There was a whole bunch of statements here. We've got A through R at this point, and we've got one that they didn't actually put in. This is from section 3.2 about determinants, which they didn't work into the main scheme here. But keep in mind that all of these statements are equivalent. They're all true for a particular matrix, or they're all false for a particular matrix. So remember D, the equation Ax equals 0 has only the trivial solution. That's what we don't want here when we find eigenvalues and eigenvectors. We want there to be more than just the trivial solution. So if there's going to be not just the trivial solution, that also means the matrix will not be invertible and not have in-pivot positions and all these other things. And particularly, if it's not going to be invertible, that means the determinant is going to be 0. Right? If the determinant's not 0, then it is invertible. If it's not invertible, determinant is 0, and that's what we're going to make use of here. We are going to try to set up our equation to say determinant equals 0. Let's see. Okay. And just in case you have forgotten, let me remind you the determinant for a 2 by 2 matrix. There's that special little shortcut, right? It was AD minus BC, and that really only works for 2 by 2s. Okay, so we need to take this matrix right here, that's A minus lambda I, and take the determinant of that and find out when the determinant is 0. That will mean that there's more than just the trivial solution. There's actually some eigenvectors and eigenvalues that do it. It's not just the 0 vector. Okay, enough talk. Let's get down to crunching numbers. So for us, we want the determinant of a minus lambda I to equal 0. So for us, that would be the determinant of a minus lambda, where the main diagonal is, the i's. Well, maybe I should write this out. 3, 2, 4, 1 minus lambda 0, 0 lambda. That's lambda times an identity matrix, and then subtract and you get this. And most of the time when I give you one of these problems, or when the book gives you one of these problems, you can probably jump straight to writing this down, and maybe even to writing down the next step, because really we know the next step is to take the determinant and set it equal to 0 and solve. And the determinant is the main diagonal, 3 minus lambda, 1 minus lambda. So the main diagonal multiplied minus the off diagonal multiplied, which is 2 times 4, which is 8. This turns out to be just a little quadratic equation. Even though it's partially factored, that minus 8 means it isn't fully factored, so we need to expand, collect like terms, and then see if we can solve the quadratic equation. So let me multiply things out here. Get to go back to your basic algebra days. So this would be 3 minus lambda minus 3 lambdas minus 4 lambda plus lambda squared minus 8 equals 0, and combine like terms and rearrange in the way we normally like quadratics. So that'd be lambda squared minus 4 lambda minus 5 equals 0. Okay, that's solvable, right? Quadratic feels comfortable. Maybe you are that type of nerd that just loved the quadratic equation when everyone else hated it. I was definitely that kind of nerd. So you can solve this with quadratic equation, or by factoring, or by graphing and looking where the zeros are. I don't care. Solving quadratics is not the point of this course. It's just a tool to get where we need to go to find eigenvectors and eigenvalues. So anyway, all that to say, I am going to factor this one, because it's easy to factor. And when factoring's easy, it's easier than doing anything else. So lambda minus 5 and lambda plus 1. Keep in mind, with that 1 coefficient on the squared term, you're looking for something that multiplies to negative 5 and adds to negative 4, which is easy enough. And then you set each of these factors equal to 0 and solve. So lambda minus 5 equals 0. Lambda plus 1 equals 0. So the eigenvalues for this matrix are 5 and negative 1. Now that we know the eigenvalues, we can go on to find the eigenvectors. And I am going to give myself a little bit of room here. Okay, so let's find one of the eigenvectors. That does mean we are trying to solve a minus lambda I x equals 0. We just solved this for lambda. Now we're going to try to solve it for x, now that we know what the lambdas are. So now let's start with 5, I guess. So a minus 5I means I'm going to subtract 5 from the main diagonal here. So it's 3 minus 5, so negative 2, 2, 4, and 1 minus 5, negative 4. Times the eigenvector equals the 0 vector. And at this point, this is just probably the easiest way to solve this is to augment and reduce the 2 by 3 augmented matrix. We know how to solve a system like this. In this particular case, the augmenting and row reducing is pretty easy, and I think I can actually just visually see that if you add one of the first column and one of the second column, you'll get 0. So I'm going to skip the in-between steps and say the solution vector here is just 1, 1. That is the eigenvector that goes with 5. There will be a different eigenvector for negative 1. But let's just check it real quick. It should be that if you multiply 1, 1 by the original matrix A, we should get 5 times that. We should get 5, 5 coming out. So as a quick little check, 3, 2, 4, 1 times 1, 1 hopefully equals 5, 5. 1, yeah, 5. 5, which is indeed 5 times the original vector. Okay, so it works. We have discovered an eigenvalue and the corresponding eigenvector that goes with it. We also need to find the eigenvector that goes with the eigenvalue of negative 1. So let me give myself a little more room here, and we'll do that one as well. This time I'll need to subtract negative 1 from the main diagonal. So this time it will be 3 minus negative 1, so 3 plus 1 is 4. And 2 is not on the main diagonal, it doesn't get anything subtracted from it, and 4. And 1 minus negative 1 is 2. And again, we're trying to solve that, coming out to be the 0 vector, and again, normally 2 by 3 augmented matrix, row reduce. Again, here I can kind of visually see that if I did 1 of the first column minus 2 of the second column, that would produce 0. So that's my eigenvector that goes with the eigenvalue of negative 1. And you could check that one too. It should be that if you multiply 3, 2, 4, 1 times 1, negative 2, that we should get negative 1 times the vector. So we should be getting negative 1, positive 2. And let's see, 3 minus 4 is negative 1, and 4 minus 2 is 2. Yeah, it works. So we have found the eigenvalues and eigenvectors for this little 2 by 2 matrix. And the general process first of all was to solve determinant of a minus lambda I equals 0. That will give you the lambdas. So maybe I should say solve for lambda. That will give you the lambdas that make the determinant 0, that make the matrix non-invertible, that make the matrix only have one or less than full number of pivots. That means there's multiple solutions besides the trivial one, which means there are actually eigenvectors. Okay, all that to get the eigenvalues. And then once you have done that, then we solve a minus lambda I augmented with 0. For each value of lambda to find the axis, to find the eigenvectors. Okay, so we'll look at, in the next video, we'll look at another example and we'll look at one shortcut, because shortcuts are good. Right? We like avoiding pain, especially pain of doing a full like 10 by 10 equation here. So we don't want to do that. All right, see you in the next video.